right, so we're thrilled to have Vladimir Koltchinskii giving the last of our plenary talks. So he's been one of the leaders in statistics for a long time, and we're really thrilled that he's here visiting us during his sabbatical. He's given, by my count, already 3 talks since we've hosted him here at MIT, so we've made him earn his stay. And I'm looking forward to this talk and the several more talks we'll ask him to give over the weekend.
Great. Thank you very much. It's always nice to be back to MIT, where I spent about 8 months, soon after I arrived to the US. Okay, it was one of the first stops in the US. Okay, I kind of decided to talk about something related to the lectures I gave before, okay, because it was hard to come up with a topic that would fit half an hour, okay. I will be talking about the following problem. We have an independent observation sample from some distribution with a known parameter theta. We will assume that theta is some high dimensional or maybe even infinite dimensional parameter of statistical model. And we want to estimate not the whole parameter, which would be a complicated problem, but just to estimate some low-dimensional feature of the parameter. And often you can represent such features as the value of certain functional that possess some degree of smoothness at the unknown parameter. Okay, and we want to estimate the value of this functional based on independent observations like this, right? Sample from the distribution with this parameter. For me personally, the motivation to be interested in this problem was, primarily related to the case when parameter is some large matrix, and we are interested in some spectral property of this matrix. We don't want to estimate the whole matrix, but we want to estimate some spectral characteristic of the matrix that is represented by some nonlinear function. Okay? But it turns out soon that the fact that this is matrix does not matter that much for what I was trying to do. Okay, so I will be in a bit. I will be. For me, the historical scale will be a bit longer than for Philippe in his talk, because Philippe started in 2014. The history started in 2014. For me, it would be a bit longer scale, about 100 years, say, okay, not 10 years, okay? And about 100 years ago, Fisher developed what we call maximum likelihood method, and one of the results that easily follow from his method and from some asymptotic theory he started developing for this method is the following result: that if we are interested in estimation of the value of differentiable function at parameter theta, then there is a very simple procedure that allows you to do it. And this procedure is just to start with maximum likelihood estimator based on this data and plug in this maximum likelihood estimator into a function we are trying to estimate. And this simple plug-in estimator already possesses some very appealing statistical properties. In particular, it is a asymptotically normal estimator. And if you take a look at the mean squared error of this estimator and multiply it by n, then it will converge to the limit variance of normal distribution. Okay, Fisher claimed at that time that this is an optimal procedure. He called this optimality asymptotic efficiency. And this claim was proved about 50 years later, and it gave precise meaning to his initial Fisher claim. Okay, it was done by Hayek and Lecam, who developed this type of lower bound that is called in statistics usually local asymptotic minimaxity. Okay, so basically the consequence of this Hayek Lecombe's theorem is that this particular estimator, plug-in estimator based on maximum likelihood method, okay, is locally asymptotically minimax, okay. So this provides a reasonable and simple solution of the problem in the case when the sample size is large and tends to infinity, and the dimension of the space is fixed, okay, is equal to 3 or 5, for instance, okay. In this case, everybody knows what to do. However, the problem becomes way more complicated if we are dealing with high-dimensional or with infinite-dimensional parameters, okay? And this initial result, based on Fisher's theory, fails in many respects, okay? First of all, it's not necessarily possible to obtain classical square root of n rates of convergence if you assume only differentiability of your function. You need, for instance, it might require more smoothness, for instance, of your functional in this setting, okay? And there is typically some threshold, okay, on the degree of smoothness, such that above this threshold you can estimate with square root of n rate, and below this threshold it becomes impossible, okay? That's one thing that is completely different, okay, in the case of infinite dimensional or high dimensional parameters. There is some phase transition in the error rate in this problem that depend on the degree of smoothness or on some other characteristic like this, okay? And secondly, there is no really simple procedure any longer. You could not just plug in maximum likelihood estimator or another straightforward estimator of the parameter in your functional and get the solution, okay? So it becomes more complicated than this. So in the recent years, it became clear, you know, that in the case of several high-dimensional models, including high-dimensional normal models, some log-concave models, and some other models, okay, the maximum of the minimax risk of the estimation, the maximum over all functionals in certain smoothness class, okay, for instance, in Hölder ball of smoothness S, for instance, okay, it has this structure, okay, and it turns out that this immediately implies, it's easy to see, that there is indeed some phase transition from classical rates like n to the power minus 1/2, depending on the degree of smoothness. So if smoothness is above this threshold, dimension is bounded by n to the power alpha, then you can achieve this rate. Otherwise, the rates are becoming slower, and in the case when smoothness is strictly above the threshold, then you can achieve even efficiency. Do the same what is possible to do in the case of small dimensions, say, okay? However, this was done only for limited number of models, some specific models, okay? I don't know how to prove it for general models. So what I will try to talk about today, I will try to show that it can be done in some way for more general models under the assumption that we are in a possession of estimator of the parameter itself, right? Such that for this estimator, kind of Gaussian approximation holds in some strong sense, right? And you can have this Gaussian approximation even in the high-dimensional setting, okay? Such estimators as maximum likelihood in finite-dimensional case are known to be asymptotically normal, asymptotically Gaussian, right? But the question is whether this property holds when dimension is becoming larger, and if it holds, then it becomes possible essentially to justify this type of bound and all their consequences, right? Like phase transition in the rates in more general setting. Okay, that will be what I will be talking about today. So I will kind of use specific estimation method based on certain iterative bias reduction. This method is not new. It goes back to the work of Hull and Martin in late 80s, okay, at least as long as this, right? But I will describe this method in completely different language, okay, not in the same as it described in these papers of the late 80s. So you can use this method this way. So plug-in estimator, if you use just our functional f and plug in, for instance, maximum likelihood estimator in f, right? It does not work in this case. Primarily, it does not work due to the fact that it has large bias, okay? When we plug in some estimator in nonlinear functional, it tends to have large bias, okay? And in high-dimensional setting, it matters. Okay, so what one can try to do, and it's kind of a rather standard idea in statistics, you can try to replace your functional f by another function, OG, such that the bias of this plug-in estimator as an estimator of f of theta will be small. Okay, and this can be phrased as a solution of finding approximate solution of certain operator equation, certain integral equation like this, and this integral operator is an integral operator with respect to the Markov kernel, and this Markov kernel gives us the distribution of our estimator theta hat for given theta. Okay, for given theta. Okay, so, you know, there is an old 19th century method of approximate solution of integral equations that goes back to Neumann, okay? It's called Neumann series method, okay? Basically, you know, you are kind of usually in the situation when operator T is kind of close to identity operator. In this case, operator B defined here is small, and you can kind of just try to invert operator T by writing this geometric series, basically, right? And then you can truncate this series, you know, just consider just the partial sum of the series for some k, and this gives us function fk of theta. This gives us function fk of theta, and then the bias of this plug-in estimator, it's a straightforward computation, can be expressed in terms of k plus first power of operator b. K plus first power of operator b. Now, in order to understand better why this type of method works in this context, one has to look at something I call bootstrap chain. Bootstrap chain is the Markov chain that starts at some theta in the parameter space, and then it has transition probability p theta a, which is the distribution of estimator theta hat, right? And this bootstrap chain can be interpreted in terms of statistical method called bootstrap, okay? So basically what we are doing, we start with first with some value of the parameter theta. We sampled our data, our observation from the distribution with this value of the parameter, and we compute estimator based on this n data points, right? We compute our estimator, and then we use estimator theta hat, right, as new value of the parameter and do resampling of the data, right? And then the estimator based on this resampling is what is called in statistics bootstrap, right? And you can iterate this procedure. You can move further, use theta hat as your new value of the parameter and do resampling again, right? Do resampling again, and so on, right? And what you generate exactly this Markov chain that starts at theta with Markov kernel p theta a in this case, right? And it's a very easy exercise to see that the powers of operator T and the powers of operator B can be expressed as certain expectation in terms of this bootstrap chain. okay? In terms of the Bootstrap chain. In particular, we are specifically interested in these powers because this is what tells us how small the error of this estimator of k of theta hat I am trying to use, right, is going to be, right? This thing can be expressed in terms of expectation of this expression, and this expression is just the case order difference of the value of our functional on the Bootstrap chain, right, on this Markov chain. Now, if we go back to kind of classical calculus of the times of Newton at least, okay, we can look at this question, you know, if we have a function of real variable and then we start at point x and started moving this point with step h, right? We can define this first order difference operator, and then case order difference will have about the same structure of as what was written before. Right, this will be case order difference. So if we iterate first order difference operator, and it is well known that if our function is k times differentiable, then case order difference will be of the order h to the power k. So basically, the question that matters here is whether the same is true if instead of this simple motion, right, just jumping along real line with step h, we have more complicated motion. We have something like this Bootstrap Markov chain evolving in the parameter space. Okay, whether similar property will hold at least on average. Okay, whether the expectation will be small in this case. Okay, so I will, as I said, I will try to study this question in the case when I'm in a possession of some estimator theta hat, such that when I subtract from theta hat theta, so I'm looking at the error of this estimator, and multiply by square root of n, then this thing is going to be close in distribution to Gaussian random variable, right? To Gaussian random variable. That will be the main assumption. I will need to quantify this assumption to kind of introduce some distance that will tell us how close they are. And kind of a typical example for me is the example when my space is just a d-dimensional space, Rd, and theta hat is maximum likelihood estimator. In this case, kind of natural normal approximation will be this, right? We just have to start with standard normal vector in d dimensions and then apply to the standard normal vector this matrix A of theta, which is the square root of the inverse of the Fisher information matrix, right? This is the limit of asymptotic limit of maximum likelihood estimator, okay, by just classical statistical theory, okay, and this will be my main example in this case. Now, we will use certain distances, as I said, right, to quantify how close to random variables, or more precisely their distributions, are in our space, okay, and in particular I will need to use for this purpose what is called Wasserstein distance, okay, so I will use it for, basically I will need it in the bounds that I will show for p equal 1 and p equal 2 only. Okay, and then I will use also this distance between distributions of two random variables. So I write it, it's more convenient for my purposes to write it as a distance between two random variables, but in fact it depends only on their distributions, of course, okay? And then this is certain variance parameters that we will get in the limit. And then the result that is possible to prove in this case is the following fact about normal approximation of our estimator fk of theta hat of our functional, right, rescaled with square root of n, how close it is to now to normal random variable, just with variance sigma f square of theta, right? As you can see in this bound, in both bounds, another bound is on L2 error of our estimator, right? How close it is to this expression, right? And in both bounds we have these Wasserstein distances that show how close our estimator is to normal, right, after rescaling. Okay, that's basically what we have in this bounds. Now, what is kind of important are consequences of this bounds. And one consequence is the following, that in the case if our rescaled estimator is in Wasserstein neighborhood of radius, of constant radius, basically of radius 1 or 20, okay, just of radius that is constant, right? This is already enough to achieve this rate that I showed you before, and as it is known from what is happening in several specific models, okay, that was known before. So you will get this rate in this more general setting, right? But under the assumption that that you have not really, you know, an approximation by normal, it should be just in the neighborhood of Gaussian vector, okay? In the fixed neighborhood of Gaussian vector. Now, in the case when the smoothness is sufficiently large above this threshold that I already showed before, and you have actually normal approximation, so this tends to 0 and then tends to infinity, we can make it small, okay, this guy. In this case, you are getting everything that is known in the classical case, right, but not for plug-in estimator, but this estimator with corrected bias, okay? With corrected bias. So this is basically the main result that I was able to obtain in this framework. Let me explain you how much time do I have, because I...
Till 1:45.
1:45, yeah. Okay. So let me explain you very briefly what, you know, how this works, why it's possible to get this type of results. So as I said before, the kind of relevant properties of these operators I am dealing with can be expressed in terms of certain expectation of our functional computed along the Bootstrap chain, right? Computed along the Bootstrap chain. Now let's assume that we have another model. This will be already Gaussian model, okay? And this will be certain model that approximates our estimator. I would denote it theta tilde. It's also some random transformation of theta, right? Some random transformation g of theta, and it's defined this way. It's theta plus theta corrupted with some Gaussian random noise, right, rescaled with square root of n here, okay? And this is this psi of theta that we need in order to approximate the distribution of our estimator theta hat, okay? So you can view it as just as a model in which you have one single observation of vector theta, right? Just one sample, basically, right? One single observation of vector theta. This vector theta tilde, and it's one observation and at the same time estimator of theta already, right? Now, we know from the conditions that theta tilde is close in distribution to theta hat, and we can quantify how close they are using Wasserstein distances, right? This is what present in the bound. Now, you can start with theta, then you have estimator theta tilde of theta, and you can create a bootstrap chain based on this estimator, right? You can use now theta tilde as new value of the parameter. You will need to generate independent copy of the noise in this case, right? And create G with this independent copy of the noise, and you can compute this G at theta tilde, right? There will be another copy of G, right? And you can, just this way, you can generate by creating independent copies, ID copies of this mapping G. You can create a bootstrap chain, right, that is based on estimator theta tilde, okay, on this Gaussian approximation, right? This chain has very simple structure. It's just superposition of some random maps, right? Superposition of some random maps. And then using the fact that theta tilde is close in distribution to theta hat, it's not that hard to prove that the corresponding Markov chains also are going to be close one to another. So this chain with tilde will be an approximation of the chain with hat, right? And you can write bounds on how close they are using this quantity that is involved in the bound, Wasserstein distance that shows how close theta hat is to theta tilde, okay? It's not that complicated exercise, but if you solve this exercise, then since the powers of operator T and of operator B and estimator of cat all can be written as terms of certain expectations, right, of our function all computed along the bootstrap chain, right? We can now use this in order to create approximation for these functions, right, and prove some approximation bounds for these functions, okay? That's basically the main idea here, and this allows us to completely reduce the analysis of our problem for this kind of more general estimator in general model to what is happening in this relatively simple Gaussian model, okay? Relatively simple Gaussian model. Now, what is happening in Gaussian model is that you can write now the corresponding operators, these powers of operator B tilde applied to function f. You can derive for them some explicit integral representations, okay? Some explicit integral representations, and everything is based just on this fact that the chain with tilde is explicitly defined as certain superposition of random maps, right, of IID random maps. Now, you know, there is, as some of you who heard my previous talks on this subject here at MIT know probably where I am heading, because there is some partial derivative involved here, and this partial derivative is the derivative of k plus one-fold superposition of some smooth functions, right? Some of them are, one is function f, and others are IID copies of G, right? The stochastic processes that we are dealing with here, right? Or some random maps. Okay, and then what we need to go back to old calculus books, okay, of 19th century and extract from this book this formula due to Fao di Bruno, right? Well, it's more complicated than this, but I'm not going to tell the story again, right? It was known before Fao di Bruno in some form, but it's usually attributed to Fao di Bruno, okay? And in our case, we just need to do some exercise that people still sometimes do in combinatorics journals, okay? Because this is a combinatorial problem when you start applying chain rule to this kind of, you know, superpositions of many functions, okay? You already see from this formula that it's a quite combinatorial object, probably, right? This Fao di Bruno formula itself, okay? In this case, it becomes a bit more complicated. You need to, but still it becomes possible to represent this operator for our problem, right? The value of this operator on function f as a certain sum over certain partition trees on the set of variables with respect to which we do differentiation, and then this partition tree can be, each of these partition trees can be labeled in certain way by some differential forms associated with our problem, and then chain rule tells you that that you can create superposition of these differential forms over the tree, and the whole thing becomes the sum of this type of expressions over all trees, right? It's a bit messy and a bit complicated, but still it's something, you know, for which you can easily then write some bounds, study the smoothness properties of the resulting functions for which we have these representations, and do all this type of exercises, right? Since we have to do it only in the case of Gaussian, only in the case of Gaussian model, because the rest is just approximation of one bootstrap chain by kind of Gaussian version of bootstrap chain, right? We can kind of rely also on Gaussian concentration inequalities in this problem, and we can obtain some very relevant bounds that allows us to study what is happening for approximating Gaussian model in this problem, right? And then using another layer of approximation, right, of one bootstrap chain by another, kind of rephrase it for the initial bootstrap chain, right, and for the initial function fk. So this is basically how it works in this paper that I wrote on this subject. It's interesting also to mention that you can use, instead of using estimator with fk here, so build on kind of actual bootstrap chain for our estimator theta hat. You can safely use estimator based on functional fk tilde that is based on Gaussian approximation and plug in your estimator theta hat inside, okay? It will have exactly the same properties as estimator based on fk, and it has computational advantage because actually to compute these operators with tilde is a much easier computational problem than to do all this bootstrap resampling, you know, that is needed in order to compute actual functional fk. Okay, this is much easier because you just need to simulate certain number of standard Gaussian standard normal vectors in RD, transform them with matrices, and then create certain superpositions. Okay, that's how it works. Okay, so it's much simpler than do resampling from some high-dimensional model. Okay, multiple times. Okay, so there is a caveat though, and the caveat is that we know very little about behavior of such estimators as maximum likelihood estimator in high-dimensional problems, okay? So the bounds that I need for this to work, right, do not really exist, okay, in most of the cases, okay? There are a few examples where I was able to obtain some bounds that are needed. One example where it's not that complicated, you can consider vectors with many independent components, okay, low-dimensional components, right? And each component is modeled by some low-dimensional model, and then the whole parameter becomes, you know, just what you create the whole parameter by combining low-dimensional parameters like this. Okay, in this case, you can get kind of normal approximation for maximum likelihood estimators of the type which is needed here, because basically we need normal approximation to hold when d comes close to n. Okay, that should be the range where d is, say, a small of n, but if we could do it only when d is like square root of n, this becomes rather meaningless, because in this regime you don't need anything but plug-in estimator. Okay. So you need rather strong Gaussian approximation properties that is not always available, although there are some results that are promising in this direction. And this result, for instance, is in the case when our estimator is just the sample mean, and we are sampling from the distribution that satisfies Poincare inequality, okay, for which Poincare inequality holds. In this case, there is this nice rate of convergence result in central limit theorem, that tells that you can get error rate in this normal approximation of the order square root of d over n. This is what we need when d is or small of n, it tends to 0, right? And there is also a Poincare constant involved in this. In particular, this can be applied to log concave measures, okay? On concave measures on RD, and luckily for myself and for many people, okay, UNC Chen was able to make major progress on what is called Cannon-Lowasz-Simonovich conjecture in convex geometry. That basically the conjecture is that for log concave vector with identity covariance, the Poincare constant is dimension free. It just does not depend on the dimension at all, but it's not known up to now whether it's dimension free, but there are bounds, there are even now slightly better bounds than bound of UNC Chen that tells that it grows very slowly with the dimension at most, okay? And this is already enough for our purposes, okay? For log concave models, you can get this type of result, okay? But beyond these two situations, I don't know much, okay? I don't think there are results that are suitable. There are examples that show that it's not always true, okay? And probably the example with many independent low-dimensional components, right, with low-dimensional parameter could be developed much further. You can assume that there is some weak dependence between components and stuff like this, and still get bounds of reasonable quality in this case. But probably you can go beyond the log concave measures also and find other situations when this type of things works. But my results here are just reduction results that shows that if certain property of normal approximation holds, right, there is a way to solve this problem, right? But I don't know to the end when it holds, and it's a separate problem of, it just adds maybe one more reason and one more modest reason to be interested in high-dimensional central limit theorem and more complicated versions of high-dimensional limit theorem, because, of course, what is done here is done just for the sample mean, right? It's just the sample, the simplest form of the central limit theorem. But if we deal with maximum likelihood estimator that is defined kind of implicitly, it becomes much harder to prove this type of result. So probably it's this type of stuff could be a good topic for a number of PhD dissertations for ambitious students, okay? Since I am not any longer ambitious PhD student, okay, I'm not working on this, so it's just open, the one who wants can grab this topic and try to do something about this, but I will stop here. Thank you.
So we've got time for a couple quick questions for Vladimir. Any questions?
Yeah.
So can anything work for infinite dimensional parameter spaces?
Well, in my, the way, I phrased it, okay, it applies to infinite dimension too, but I have not worked on any specific examples. The thing I need these conditions. Basically, dimension in my case is some upper bound on the Hölder norm of this Gaussian process, okay?
How reasonable it is to expect the Gaussian approximation?
Sorry?
How reasonable it is to expect Gaussian approximation?
In infinite dimension.
Yeah,
well, central limit theorem holds in infinite dimensional spaces, right? So you can expect something, okay, like this, okay? It depends, okay? It kind of, in infinite dimension, of course, you are not using dimension, you are using different complexity measure, okay? But the questions are the same, okay? There is, by the way, another thing related to this that I maybe should mention, here at MIT, Viktor Chernozhukov did quite a bit of work on convergence rates in high-dimensional central limit theorem, and he was proving this type of results. He was sacrificing, instead of having 1 over square root of n rate in the central limit theorem, he was sacrificing this rate, going, maybe to n to the power 1/6 or something like this, and then he was getting logarithmic dependence on the dimension. But the type of results he proved was this. He was looking at kind of the distance he used to measure normal approximation was supremum over some hyperrectangles, say, okay, some cubes essentially, or parallelepipeds, okay, in high-dimensional space in fixed coordinate system, okay. If you kind of think about this in terms this problem set here, okay, it would mean that you probably should use, instead of L2 norms that is used, Euclidean norms that is used in these results, you know, in terms of Poincare constant, you should use L infinity norm. But if you use L infinity norm, then the norm of the square of Gaussian process could easily become like logarithm of d. Okay, so instead of d in your bounds, you should have now logarithm of d. This will be correct complexity parameter, right? And then you need something like logarithm of d is O small of n, and you have normal approximation. This is not what Victor was able to prove. Okay, he had much weaker results than this. Okay, so you had logarithm of d maybe O small of n to the power 1 over 10 or something like this. Okay, but not O small of n. Okay. In order to prove so it's kind of, you know, there are many questions that one can ask because all this depends on which norms we are using in the space, you know, and you can have different results based on this also.
Any more questions? Yeah.
Yeah, so can you clarify, so when you say we don't have enough of those like high-dimensional approximation results, is the difficulty, and so, you know, like you showed this Fatih et al. Result, where, you know, so where's the difficulty? Is it the Wasserstein bound, or is it the fact that you want to have, like, for example...
Well, the results of Fatih was proved using Stein method, okay, and kind of non-trivial facts about Stein kernel, okay, that's how it was, you know, it took a while before this rate was achieved, okay, so there were several attempts, you know, to do this, but it took a while before this rate was achieved, okay, so it's...
But that's because it was under the class of just finite...
It was under the class, in the class of distribution for which Poincare inequality is satisfied, okay? So it's known for long since the 80s that you need some assumptions on the distribution in order to have this type of rate, okay? In order to keep normal approximation when d is, say, O small of n, okay? You need something, it's not automatic, okay? There are some relatively easy examples that show that you can break it easily, okay? And not have normal approximation, you know, unless maybe d is like n to the power 1/2 or smaller than n to the power 1/2, okay? But for some models it's possible, and the question is whether one can identify some natural classes of models, right, for which this technology would work, okay, and would give what is needed. I cooked up some examples, but these were just some examples to put in the paper in order to be able to claim that it is good at least for something, okay? And it was based on what I was able to extract from the literature, basically, right? But the problem itself is an interesting problem.
You mind if I ask one more?
Go for it, yeah.
Okay, so at some point you mentioned I understand computational complexity is not something that keeps you awake at night, but...
No, not at all. Yeah, I sleep well, yeah.
I just want to make sure that I understood, because you said that using the Gaussian approximation was simpler than using the chain of Bootstrap. Is it at the level of your claiming?
You know, imagine what you need in order to implement Bootstrap chain in this case, right? You will need this. You will need to, okay, you have your data and observations, for instance, I don't know, 1,000 observations, okay, sampled from some distribution, usually in high-dimensional space, right? Then you compute your estimator of the parameter based on this data, right? Then you have to use this estimator as a new value of the parameter. And you have to resample 1,000 observations again, right, from this data, right? from the distribution with this estimated parameter, right? Then you have to compute based on this Bootstrap sample, right? You have to compute Bootstrap estimator and repeat it again and do it, if you have 10 times differentiable functional, do it 10 times, okay? But then, since you next you will need to use Monte Carlo in order to compute these expectations that gives you these functions BKF of theta, right? Of theta hat, say, right? You will need to repeat it multiple times, right? In order to apply Monte Carlo to estimate the integral. Okay, so it's time consuming. It would require a sampling of 1,000 observations from some high dimensional distribution and doing it many times. And Gaussian, in the Gaussian case, in order to compute this function fk tilde, you will need to do this, right? You will need to, you have metrics, the inverse of Fisher information matrix for your models that you know, right? You can compute for any theta, right? You can compute this matrix for any theta, right? Square root of the inverse of the Fisher information. Then you simulate standard normal vector, right? Simulate standard normal vector. Then you apply this matrix, right? And you compute theta plus this, right? Then you use this as a new value of the parameter and do this computation again, simulating one more copy of vector, right? Then again, you will need to create more copies, right, in order to do Monte Carlo, right? In order to, at least I don't know how to do it without Monte Carlo, right? You have still to do this, but you don't need to resample 1,000 observations any longer, okay? Each time, right? In each round of this Monte Carlo, you won't need to resample 1,000 observations, right, in order to do this, right? You will need just to create a certain number of copies of standard normal vector in d-dimensional space, and you can do this computation. So it's significantly better, okay? If one really does not sleep at night, you know, and wants to compute something, it's better. I don't know, it's still involved, but it's much better. Okay.
Some people have counting sheep and others have Monte Carlo approximation to fall asleep, so I've learned a new trick to fall asleep. So thanks for joining us for SDSCon. I just wanted to say thanks again to the speakers for the great day of stimulating talks, and I hope we can continue the conversation around the Institute. So thanks, everyone.